Welcome back. We are finally about to talk about the rocket part of rocket science. So from the past module, we now know where satellites orbit around Earth. They are not randomly distributed, but instead are found in three main regions: low Earth, medium Earth, and geosynchronous orbits. And we've discussed the super fast horizontal speeds needed to achieve orbit. For low Earth orbit, the required speed is 17,000 miles per hour. So that's like 100 times faster than a Formula One race car. So in the next few segments, we'll focus on how to achieve these crazy high speeds. We'll discuss how rockets work, different types of rockets and rocket fuel, and we'll talk about my most favorite equation, the rocket equation. So sitting here at rest on Earth, I'm going to need a lot of force, a lot of oomph to get off the ground to reach those speeds needed to achieve orbit. And spoiler alert, we're going to use rockets to generate this force. How much oomph we need to get off the ground depends on a couple things. The first is a destination. Where are you going? Are you headed to low Earth or geosynchronous? Maybe you're headed to Moon or Mars. This will set the speed required to stay in orbit to reach your destination. The second thing to consider is your payload. How much stuff are you bringing with you? And you can imagine it'll be more difficult to launch with a very heavy payload to the same destination. Regardless of your choices, the speeds we need to launch a payload into orbit are huge, and that brings us to rockets. Rockets are used to propel a payload to its destination. But why rockets? Why not something else? Let's do a comparison of rockets to a more familiar mode of transportation, airplanes. And so, by way of review, let's compare airplanes to a low Earth orbit satellite. And to organize what we know, let's make a chart. For this comparison, let's look at the height above the Earth's surface, the speed, and whether or not the engine is running for both airplanes and satellites. First of all, how high above the Earth's surface do both of these things fly? Well, if you're in an airplane, you might hear your pilot get on and say, I'm going to turn off the seatbelt sign now that we've reached our cruising altitude of 32,000 feet. This is equivalent to 10 kilometers above the Earth's surface. And in comparison, a low Earth orbit satellite is 50 times higher at a height of 500 kilometers above the Earth's surface. We can also compare the speed at which these two vehicles move. Airplanes fly at about 500 to 550 miles per hour. That's 0.2 kilometers a second. And we've previously calculated that a low Earth orbit satellite, in order to maintain its orbit, is moving at 7.5 kilometers a second, or 17,000 miles per hour. So think of an airplane on the tarmac and a rocket on the launch pad. The rocket has much farther to go and needs to achieve much higher speeds to achieve its goals. So the next thing to consider is what creates the motion. That is, why are these objects moving? For an airplane, once the engine turns on, once you start taking off, the engine remains on through the entire flight. For satellites, this is really different. The engines are only on when you want to achieve orbit, that is, during launch. Once you're in orbit, you're in free fall. You don't need power and you don't need to turn on your engines unless you want to change orbit. So once in orbit, a satellite is moving passively without its engines on. This is really, really different and interesting compared to airplanes. To understand this difference, we need a way to think about motion. That is, why do rockets and airplanes move at all? That is, we need a framework to think about how these things move in the first place. The framework that we're going to use is Newton's laws of motion. So, in 1687, Sir Isaac Newton proposed 3 rules for how things moved, and he published a book on them written in Latin whose English translation is The Mathematical Principles of Natural Philosophy. It's one of the most influential works in all of science. These rules explain most of the motion in our daily lives, and these rules are called Newton's laws, and we'll talk about how they pertain to rockets. Okay, Newton's first law says formally, if no force is acting on a body, the body's velocity cannot change. Less formally, this means that an object at rest stays at rest unless it's acted on by a force. That is, if there is a ball sitting on the ground, it's not going to move unless a force acts on it. In this case, the force is like someone kicking it or something. We're going to go out of order and talk about Newton's third law before coming back to the second. Newton's third law says that the force of bodies from each other are equal in magnitude and opposite in direction. Less formally, every action has an equal and opposite reaction. And this one is going to be useful to us. Imagine that you have a balloon full of air, and you let go of that balloon. Air rushes out the balloon in one direction and pushes the balloon forward in the opposite direction. That is, there's an equal and opposite reaction. The amount of air and how fast it's moving completely determines how the balloon is going to move and where it's going to go. So that brings us back to Newton's second law. This law provides a way to quantify how much the balloon or my rocket will actually move. Newton's second law states that the net force on a body is equal to the product of its mass and its acceleration. So, this is an equation. So this equation says force equals the mass times the acceleration. And this equation is best understood by an example. So imagine I have a bowling ball and a wiffle ball. So the bowling ball is super heavy while the wiffle ball is really light. And if I apply the same amount of force to these two objects, that is, if I kick each of them with the same amount of effort, the results are going to be really different. So if I kick the wiffle ball, I might get it moving across the room. If I do the same thing to the bowling ball, it might move like a few inches. Another way to say that is, for the same force, a massive object will accelerate less. Or it takes more force to accelerate something that is more massive. And you can imagine this in terms of rockets. So the more stuff you want to launch up, the harder it's going to be to reach the speeds needed for orbit. Okay, so coming back to the image of a rocket, Newton's laws are in action right at the base of the rocket where the rocket exhaust stuff is coming out. Newton's third law says that if you push stuff out in one direction, it will propel the object in the other. So if I push rocket exhaust out the rocket in one direction, the rocket will move in the opposite direction. Newton's second law says that you get more force if you have more exhaust mass, the more stuff coming out, or if that exhaust is leaving the rocket faster. And these two ideas from Newton's laws are something that we're going to come back to several times in the next few segments. These ideas will guide our understanding and design of rocket engines. I still really haven't answered the question of why rockets, and in the next segment we're going to dig deeper into this questioning by continuing to compare airplanes and rockets.